Swayam Prabha. Digital India. Educated India.
Hello everyone. So we were talking about the filtering operation applied to the Fourier modes, isn't it? So we had U bar here represented as a discrete Fourier transform. So you would have U bar of x be equal to Cn bar of e to the I kappa n x, and summed from 1 minus half n max to half n max. So this n max is corresponding to the maximum number of grid points required to fully resolve u of x. Okay. However, the u bar, which is the filtered velocity field, is corresponding to the filtered Fourier mode. And how do you obtain that filtered Fourier mode? By taking the transfer function g hat of kappa and multiplying it by the Fourier mode corresponding to the fully resolved velocity field. I hope you're understanding. So Cn bar is g hat of kappa multiplied by Cn. Now, what does g hat depend on? That depends on the kind of filter that you select. And that is what we are going to be discussing today. So if you have the sharp spectral filter, so consider first the sharp spectral filter with a cutoff wave number kappa c less than kappa max. Obviously, the cutoff wave number is going to be less than kappa max. Kappa max is the maximum resolved wave number to resolve the Kolmogorov scale. Kappa c is your cutoff wave number corresponding to LES. So it will be somewhere in the inertial subrange, it will be less than kappa max. So we know kappa c is going to be less than kappa max. Now, if you choose kappa c in such a way that n, which is the number of grid points in your LES grid, then n is equal to kappa c L over pi, which is going to be, let's say it is an even integer. And then you have let's say you have a sharp spectral filter. So that means g hat of kappa would be equal to a Heaviside function, isn't it? In spectral space, the sharp spectral filter is a Heaviside function. In physical space, a sharp spectral filter is a sinusoidal function. So this is now a Heaviside function in spectral space. So it would be h times kappa c minus kappa magnitude. And in that case, if you have a sharp spectral filter, what does it do? It basically removes all the wave numbers greater than kappa c. So Cn bar would be equal to Cn for n less than half n, right? Cn bar would be equal to Cn for n less than half n, and Cn bar would be equal to 0 for n greater than half n. Remember, in LES, your maximum number of grid points is n. That means on one side, because wave numbers are taken from negative to positive, so on one side it is basically half n. Following me? We did this in direct numerical simulation. We're doing the same thing here. So because the sharp spectral filter is easier to discuss here and is easier to understand in the context of all of this, we picked this filter, and you can see how it is easier to make the point here of Cn bar is equal to Cn, meaning until the kappa c, right? Until your grid points corresponding to LES, until your cutoff wave number, the Fourier modes of LES and DNS are the same. Are you getting me? But beyond kappa c, it is just 0, because it just completely removes all wave numbers greater than kappa c. So what we have done is, we have taken, now if you had a fully resolved field, you would take everything up until kappa c. And beyond kappa c, you would consider that to be 0. That's essentially what we are doing here. Cn bar is equal to Cn. This is a fully resolved field. This is an LES field. Cn bar would be equal to Cn up until kappa c, or n less than half n, which is basically the same as corresponding to a kappa c wave number, and Cn bar would be equal to 0 beyond that, because you only have it resolved until then. N is your maximum grid points anyway, till LES. There's nothing beyond n. There's nothing beyond kappa C. So Cn bar would be equal to 0. So I hope this is clear. In that case, your U bar of X is now defined as the same as your fully resolved field, except now you're only summing from 1 minus half n to half n. So it is not 1 minus half n max to n half n max. It is 1 minus half n, because beyond n you are just annihilating, you are destroying, you are removing all the wave numbers, right? When I say n, I mean corresponding to the cutoff wave number. So you might as well keep the Fourier modes as Cn. You do not keep it as Cn bar, because Cn and Cn bar are the same until kappa C. So I hope this is clear. So that is what we have done here. U bar of X is summation n 1 minus half n to half n Cn I to the I kappa n X. Okay. So now you have this a resolved field, actually a filtered field on this grid that has a maximum number of grid points of n. So n max is gone, kappa max is gone. You now have n. You have n. You have kappa c. Those are your number of grid points and cutoff wave number respectively. And now you have an H, which is your grid spacing corresponding to your LES grid. So corresponding to the grid that has a maximum number of grid points of n in each direction. So H is equal to box size divided by n. So that is L over n, which is basically equal to pi over kappa c. So see, you now have the grid size corresponding to your cutoff wave number. Now with that as the background, you can choose your filter width delta to be equal to pi over kappa c. Delta would be equal to pi over kappa c, because delta would be the same as h. It has to be equal to or greater than h, right? It doesn't make sense for it to be less than h, because your grid spacing, you want it to be as close to possible as delta, but at the same time not greater than it, because you won't be resolving anything less than h. Following me? You're not resolving anything less than h. So your grid spacing is your benchmark. So it has to be equal to or less than delta. So in most of the cases you choose delta to be equal to h. So that is why we are writing delta is equal to pi over kappa c. So what have we learned? So the filtered field given by the sharp spectral filter represents n is equal to kappa c L over pi Fourier modes, or equivalently by the n values on a grid spacing h is equal to delta pi over kappa c. More Fourier modes or more grid points provide no further information, right? You have more number of grid points, it is not going to provide any other information, because you are cutting it off at kappa c anyway. If you're cutting it off at kappa c, so that's like saying, if you're cutting it off at delta in physical space, if your filter width is delta, having h less than that doesn't make sense. I mean, you are wasting computing resources. You should not have it greater than delta, that is for sure. H should be equal to delta or less than delta technically. But it doesn't make sense to have it less than delta, because you're not resolving anything more, because you're resolving only until delta. You are resolving only until kappa c. So anything beyond kappa c is just wasted resources. So I hope that is clear. So now let's take that whole concept and take it into 3D, because so far we've been looking at filtering in just 1D. We've been looking at a 1D variable and see what that how the filtering works, and that is okay. In order to understand this better, we did that. So let's take and apply this concept, the same thing, into 3 dimensions. So for the general case, the filtered velocity field can be defined in terms of g of r of x. So as you can see, u is in bold because it is 3D. X is in bold because it's a 3D space. U bar is a filtered field, which is also 3D, of course. And the filter function g of r of x, in general, it could be a function of r and x. So it could be uniform, non-uniform, it could be isotropic, it could be anisotropic. Now, any filter that we have seen before, all the examples that we have seen before introduced in 1D can be applied to isotropic, can be applied to used to generate uniform isotropic 3D filters. So the box filter basically becomes a volume average over a sphere of radius delta over 2, and the sharp spectral filter removes all wave numbers corresponding to a wave number magnitude greater than or equal to kappa c, isn't it? Kappa in bold magnitude of kappa wave number vector is has to be greater than kappa c is basically removed. So most of the results that are obtained in 1D carry through basically straightforwardly into 3D filters. So for example, if you think about homogeneous turbulence, the filtered energy spectrum E bar of kappa is G hat of kappa squared times E of kappa. So can you tell me, are you able to figure out why is this squared here? I have G hat of kappa squared times E of kappa. Why is that? That is because I have my energy spectra calculated as velocity squared. Kinetic energy is U squared, proportional to U squared. So you are taking the filtered velocity twice. That means, and multiplied, right? So that means your transfer function will be squared. So it is the transfer function squared multiplied by E of kappa. That's the reason. So if you use that, you will realize that 80% of the kinetic energy is resolved if the width is taken to be 1.2 LEI. So slightly larger than LEI, you will get 80% of the energy. You will resolve 80% of the energy for a sharp spectral filter, and delta equal to 0.8 LEI for a Gaussian filter. In that case, if you choose these as your numbers, as in delta being equal to 1.2 LEI and for a sharp spectral filter, and 0.8 LEI for a Gaussian filter, you will resolve 80% of the energy. You will not resolve 20% of the energy, but you will resolve 80% of the energy. Whether that is sufficient for your problem, that depends from problem to problem. If you have inhomogeneous flows, you might have an anisotropic anisotropic uniform rectangular grid with grid spacings going from H1 in one direction, H2 in the other direction, and H3 in the third direction, right? So then you would need an anisotropic filter with a characteristic filter size or filter widths of delta 1, delta 2 and delta 3 in the three directions, respective directions, and then being proportional to H1, H2 and H3. In that case, you could choose a uniform filter width to be equal to delta 1 times delta 2 times delta 3 to the cube root. That's one way to do it. So you could have a characteristic filter width chosen like that. So that's one way to do it. Now, from the filtered velocity field, we can then form filtered velocity gradients, del u bar del xj. And in that case, the filtered strain rate is given by this. Sij bar is half times del xj ui bar plus del xi uj bar. Now, the reason why we have moved to filtered strain rate is we are getting to the point where we are going to be deriving the filtered equations. When we derive the filtered equations, we will realize that there are some unclosed terms that are going to pop up, and those are going to be related to the strain rate. If you remember, when we derived the Reynolds equations, what did we do? We applied the Reynolds decomposition, then we averaged out the equations. And when we did that, the unclosed terms popped up. What were those unclosed terms? The Reynolds stress. In order to close those equations out, how did we express the Reynolds stress as? We expressed it as a function of the strain rate tensor based on the Bissonnet's hypothesis. Bissonnet's hypothesized that the Reynolds stress would be proportional to the mean strain rate. So here, that is where we are going. Eventually, when we filter out the equations, and we will see that when we filter out the equations, we will see that some unclosed terms will come up. Those are basically the residual stress tensor. Just like you had Reynolds stress tensor, here you will have the residual stress tensor. That residual stress tensor will have to be closed. How do you do it? You invoke the Bissonnet's hypothesis again. You equate it as, you represent it as being proportional to the filtered strain rate. And that's the reason why we are doing this. So let's see what the filtered rate of strain looks like, or filtered strain rate looks like. It is Sij bar is is equal to half of del xj ui bar plus del xi uj bar. Okay. Now any tensor, if you want to calculate the magnitude of it, would be given by the characteristic filtered rate of strain is given by this S bar is equal to 2 Sij bar to the half. and any tensor's magnitude is calculated like that, and that's exactly what I've done here. This is the magnitude of the rate of strain tensor. Remember, rate of strain is a tensor, Sij. It is Sij bar, it is filtered rate of strain. So I'm calculating the magnitude of the tensor by taking 2 times Sij bar, the whole thing to the half. Both of these are going to be useful and prominent in the derivation of subgrid scale models coming up later. Okay, so keep that in mind. Now, let's consider high Reynolds number isotropic turbulence. Obviously, it is going to be high Reynolds number moving forward because we are talking about doing large array simulations. We have to invoke the Kolmogorov's hypothesis, which is applicable only to high Reynolds number. So it has to be high Reynolds number. So let's consider high Reynolds number isotropic turbulence, and then we know that the energy spectrum function in the inertial subrange looks like this: C epsilon to the 2/3 kappa to the minus 5/3, right? It is a function of kappa to the minus 5/3 in the inertial subrange. So E of kappa adopts this function according to the Kolmogorov's hypothesis: C epsilon to the 2/3 kappa to the minus 5/3, and C is a universal constant. Now, if you calculate the mean square of S bar, as in S bar squared mean, okay, S bar squared mean. So here, again from here, if all I'm doing is just squaring it and then taking a mean of it, okay, I'm squaring it and taking the mean of it, what I get is 2 Sij, and since I squared it, the square root went away, and then I have a mean, and that's what I have: 2 Sij, 2 Sij bar, mean. Okay, this mean represents time average. Now, here is where I'm invoking something else. This is actually related to the dissipation rate divided by kinematic viscosity. I'm not going to go over the derivation, but the characteristic rate of strain, okay, the square of the characteristic rate of strain, which is 2 Sij bar mean, is given by the dissipation. It's proportional to the dissipation. So that is dissipation divided by viscosity. So then what you will get is 2 times, and the way we have defined dissipation earlier in terms of the energy spectra gives you this equation, because epsilon is equal to integral 2 nu kappa squared E of kappa d kappa, isn't it? 0 to infinity. This was the dissipation. So now you divide by nu, and then this is what you get: 2 0 to infinity kappa squared E bar of kappa d kappa. So then what you have is, you will have 2 times 0 to infinity, and instead of this filtered energy spectrum, I will write this as kappa squared g hat of kappa squared times E of kappa. Okay, so keep in mind there is one minor correction, that there wouldn't be a factor of 2 here because the 2 is already included here. But again, that's what it is. So the dissipation divided by viscosity. So I believe it is this epsilon divided by 2 nu. That is what this filtered strain rate is. Okay, so you divide by the 2, and and epsilon itself has got a 2, so that 2 and this 2 gets cancelled, and this 2 gets moved on to this step here. So now it is clear. So epsilon divided by 2 nu is the characteristic rate of strain. So basically the 2 Sij bar and a mean of that. So that is characteristic rate of strain squared. So you will have 2 times 0 to infinity kappa squared filtered spectrum times d of kappa, and the filtered spectrum you would write it as g hat of kappa squared times E of kappa, because we saw that earlier, right? And this is what you have. Now think about this. The characteristic rate of strain squared is 2 times 0 to infinity kappa squared g hat of kappa squared E of kappa d kappa. Let's think about this equation. Now, as kappa gets larger and larger, this term starts to become more prominent. For smaller kappa, this is a very small number, because for small kappas, kappa squared is an even smaller number. So for smaller wave numbers, this term is not as dominant. It starts to be more dominant as kappa gets larger and larger. So you would agree that this term gets more dominant at larger wave numbers. On the other hand, I have chosen my wave cutoff wave number such that it is in the inertial subrange. My cutoff wave number is in the inertial subrange. I saw that through the spectra earlier. So you should be able to agree with me that this is more dominant in and around the kappa C. Because beyond kappa C it is going to be 0. Right? So I am integrating this from 0 to infinity, but the truth is this only needs to go until kappa C, because beyond kappa C it is 0. And in fact, since the term is getting more and more dominant for larger wave numbers, it is getting more and more dominant in and around kappa C. You would agree, right? So the characteristic rate of strain squared is essentially only dominant in and around kappa C or in the inertial subrange. Everywhere else it can be neglected, because for lower wave numbers kappa squared is an even smaller value. So this entire term will be a very small value, so it can be neglected. Whereas for larger wave numbers it is going to be more dominant, and there is nothing beyond kappa C. And so as it gets closer and closer to kappa C, this becomes more and more dominant. So the characteristic rate of strain is more dominant in the inertial subrange. So that is what we are trying to describe here. In which case you can substitute the filtered energy spectrum with the inertial subrange spectrum. So what can you do? So if that is what we mean here, if the cutoff wave number kappa C is in the inertial subrange, the integral in the above equation can be well approximated by substituting the Kolmogorov spectrum for EF kappa, which means the characteristic rate of strain squared is approximately equal to 2 times 0 to infinity kappa squared G of kappa squared, isn't it? G of kappa squared, this term, times E of kappa, which is what? In the inertial subrange, according to the Kolmogorov's hypothesis, it is C epsilon to the 2/3 kappa to the minus 5/3. D kappa, of course. And here is where I am invoking some algebraic manipulation. So what I'll do is, I will take C like this, epsilon to the 2/3, and look at what I've done here. I have delta to the negative 4/3. The reason I did that is you brought in a new function AF, and I'll come to that in a bit. But I'm defining that AF as 2 times 0 to infinity kappa delta to the 1/3 G of kappa squared delta D kappa. Now this is my motivation for doing it. So earlier, whenever we were looking at energy spectra, I always presented energy spectra in a scaled form. Energy spectra was scaled on the y-axis, but even on the x-axis, I've always not just looked at kappa. I've always normalized it with either the integral length scale or the Kolmogorov length scale, mostly the Kolmogorov length scale, right? So we always had kappa eta, kappa 1 eta, or kappa L11. So in LES, the analogous characteristic length scale that we have, especially since we are considering the inertial subrange, what is more dominant? The filter width. So what I want to do is, I want to scale my wave number in such a way that I'm scaling it with delta, because that is the dominant length scale here, isn't it? Eta doesn't matter, the Kolmogorov length scale doesn't matter in LES. You're not resolving any of those, you're just modeling those using subgrid scale models. The large length scale, yes, does matter, but what is more important in LES is what is your filter width, because that determines where you stop. That determines where you're stopping to resolve. That determines until what length scale are you resolving. So delta is what matters. So naturally, I would scale my wave number with filter width, and that's what I'm doing. So in order to do that, I have a kappa here. So I want to scale that kappa by multiplying it with the delta. And then I also have a kappa squared times kappa to the minus 5/3, isn't it? So that becomes kappa to the minus 6 minus 5, kappa to the 1/3. It becomes kappa to the 1/3. So in order to have a kappa to the 1/3, in order to scale that, I would need a delta to the 1/3. So I would have a delta to the 1/3, and another delta from here. So delta to the 1/3 multiplied by delta, that becomes delta to the 4/3. This is what I need to multiply it with, which means I need to divide by that as well. That is where this is coming from, delta to the negative 4/3. So I have AF C epsilon to the 2/3 delta to the minus 4/3. And so then I would define AF as 2 times 0 to infinity, the rest of the terms, which is kappa delta to the 1/3. So as you can see, I have scaled this, times g hat of kappa squared, that's just the transfer function squared, and in delta d kappa, which is basically d of kappa delta. This is the same as d of kappa delta, isn't it? That's essentially what it is. So what I've done is I have just scaled kappa with delta, and I have written it. So what I've obtained an expression for the characteristic rate of strain squared, which is AF times C epsilon to the 2/3 delta to the minus 4/3, and AF defined like this. We will get to what we do with AF later when we derive the subgrid scale models. But for now, keep it as it is. This analysis was started by Lilly in 1967, and this was the beginning of the development of subgrid scale models. We will look at that development in the next class. Thank you.